Welcome back, student. In the previous lecture video, we already discussed that what the fuel and combustions, the different types of fuel, that is solid fuel, liquid fuel, gaseous fuel, and what is the solid, liquid, and gaseous, and what are the advantage of solid fuel over liquid fuel, what are the advantage of gaseous fuel over liquid fuel. So, these are the topic already we covered in the previous lecture video. Now, we will discuss on the theoretical and excess air and stoichiometric ratio, equivalence ratio, and the heat of reaction. Okay, fast law analysis. So all those things will be discussed in this lecture video. Now, the theoretical and excess air. Now, as you know that for any type of combustion of a fuel, they are required a particular means they are required actually sufficient amount of oxygens. Otherwise, the combustion will not take place. So oxygen is required, but that oxygen in the air is present in a particular mass basis as well as volume basis. Now, what is theoretical air and what is excess air? Theoretical, the name suggests that the air required for the fuel, the air required for the combustion process is basically theoretically, and in case of excess air, basically it indicates the amount of there are some difference in between theoretical and practical. That amount is basically uh, excess amount. Okay, now what happens here, theoretical and excess air, that it is the minimum amount of air that supplies sufficient oxygen for the complete combustion of all constituent element of the hydrocarbon in fuel, like as you know, for methane, ethane, all these types of, as you know, the gaseous fuel. There are others also. uh, Gaseous fuels are there, in which their carbon and hydrogen are present, and they are required for oxygen to complete combustions. But the amount of oxygen which is required for the complete combustion of all these constituent and get to this and oxidize that particular air is called basically theoretical air. But in practice it is not happen. In practice, the amount of air which is required for the complete combustion is greater than the theoretical air. Okay, so it is basically this amount of air which is required greater than theoretical air, that is basically called excess air, which is not which is not actually theoretical air, but it is required excess amount of air for the complete combustion. So that's why this air is called excess air. Okay, and as you say that if you write down here 150% theoretical air, that means air actually supply is 1.5 times the theoretical air, because for the complete combustion amount of air supplied, that is basically excess air, is obviously greater than theoretical air. Okay, now if the amount of excess air, amount of air supplied actually in practical cases, suppose that is 150%. Okay, but theoretically is 100%. So theoretically air which is required, that is 100%, but amount of air which is required in practical cases, that is 150%. So amount of excess air, that will be 150 minus 100%, that is 50% is your excess air. Or you can say in this text of that theoretical or excess air, that 150% theoretical air means the air actually supply is 1.5 times the theoretical air. Okay, similarly, if you can give example on theoretical exercise, suppose it's a reaction with methane, that is CH4 plus 2O2 plus nitrogen, that is present basically atmospheric nitrogen. Okay, that form is CO2 plus 2H2 plus 2 into 79 by 21 into, when we are not introduce the actually excess air, so that this is without excess air. Now, if you if we assumption that there are some amount of excess air are present for the complete combustion, that will be 2 into here O2, that will be 1.5 O2, because it is theoretical air. Okay, but in practical that will be 1.5 times of theoretical air, that means 1.5 O2 plus 2 into 79 by 2 into 1, because in oxygen there are also some nitrogen also present, so that's also it will be also 1.5 times. Okay, CO2 plus 2H2 plus 2 into 79 by 21, okay, into 1.5. If it is multiplied by 1.5 into 2, that will be 3, that's why a 3 here. Okay, so when you consider there are excess air is present, because excess air is required for the complete combustion. Otherwise in practical cases the incomplete combustion takes place, which is not desirable. So for the complete combustion, all the constituent element means in the hydrocarbon of fuel, that may be carbon, hydrogen, and other element should be fully, actually should be totally complete combustion takes place. Okay, and these are the desirable properties. These are the desirable conditions for any type of combustion. So these are the concept of theoretical and excessive. Okay. So stoichiometric air-fuel ratio. Okay, it is sometimes also called chemically correct mixture of air fuel. So stoichiometry basically the chemically correct air and fuel mixtures so that so that the complete combustion takes place. So these are the main conditions that complete combustion should be takes place, and it should be chemically correct required air and as well as fuel ratio. Because for the combustion of fuel, there is required of air, obviously. Otherwise, combustion will not take place. For to do this, there are some correct mixture are there so that the full incomplete combustion takes place. So that mixture of air and fuel is basically called stoichiometric air fuel ratio or chemically correct air fuel ratio. Okay. Now, in this particular mixer, on a particular mixture of air and fuel, there are some percentage of fuel are there, there are some percentage of air required, which is required, that is the mixture. But in a particular mixture, if the percentage of air is very less, okay, and the percentage of fuel, the presence in a particular mixture is very high, then the mixture is called rich mixture. Now, if any mixer has an excess amount of air compared to the fuel amount present in a particular mixer, that is called weak mixer. Okay. Now, already we discussed the theoretical and excess air. That theoretical air is the air that is which is required for the in air that amount of oxygen that present. Okay, which is basically used to complete combustion. That is basically theoretically that is called theoretical air. And in case of in practice, that is not possible because for the complete combustion they are required as much as greater than the theoretical air for the complete combustion. So this amount of air, actually the percentage of air required in practical cases and percentage of air required in theoretical cases, this difference is basically excess air. Or you can say that the theoretical air is basically 1 point. If the theoretical air is 150 150 percentage of theoretical air, it suggests that it means that 1.5 times of theoretical air, because 0.5% is your excess air to complete the combustion. Okay. Now, percentage of excess air also calculate this formula, that actual air fuel ratio minus stoichiometric air fuel ratio divided by stoichiometric air fuel ratio. Okay. So in this way also you can calculate the amount of excess air required for a particular complete combustion of a fuel. That fuel may be methane. When the methane react with the oxygen or ethane or octane, so all this fuel which is react with the oxygen, there are some amount of oxygen is required for the complete combustion takes place. There are some amount of others air that is called excess air. You can calculate from this formula also. Okay. From this expression also, actual air fuel ratio minus stoichiometric air fuel ratio divided by stoichiometric air fuel ratio. Okay. Now the next topic is the equivalence ratio. Equivalence ratio is generally defined as the term that is phi. Now phi is the ratio with air fuel ratio of stoichiometric divided by air fuel actual, or in other form also it also suggests that equivalent ratio is a ratio of fuel air ratio of actual divided by fuel ratio of stoichiometric. Okay, and this is the equivalence ratio. Now equivalence, if the equivalence ratio of phi is equal to 1, that means it is a stoichiometric ratio, that means a chemically correct mixture. Okay, now if phi less than 1, that means it's a less fuel is required, and that mixture is called lean mixer. If there are less fuel is required are present, actually that is called lean mixer. If there are more fuel are present, that is phi is greater than 1, then it's called rich mixer. Okay, so equivalent ratio is the air fuel stoichiometric ratio divided by air fuel actual ratio. So depending on the value of phi, you can call it as a stoichiometric or lean mixer or rich mixer. In a lean mixer, the percentage of fuel is very high, means is very low, because there is in chances of maximum amount of, or there is chances present of excess air. Okay, but in case of rich mixer, there is a high percentage of fuel present compared to the air, because there are some deficiency of air in case of rich mixers. And stoichiometric ratio, in which the air fuel ratio, that the ratio of air fuel mixture is very stable, means correctly the chemically correct air fuel ratio are present, that means phi is equal to 1. So this is the equivalence ratio and this is the significance. Now let's take an example to calculate the air fuel ratio. Theoretically are used an equivalent ratio and percentage of excess air, which amount of percentage excess air is used, you can calculate. So let's take a numerical. Okay, octane is burned with a dry air. Okay, first of all, octane is burned means octane is react with the oxygen with dry air. Then volumetric analysis of product on dry basis, that percentage of the volume is given that 10.02% oxygen, carbon monoxide and nitrogen. So these are the product, and reacted is your octane and oxygen. Okay, octane and oxygen, because it is react with the oxygen because the fuel is your octane, and react with your oxygen because in dry air there are oxygen is present and there are some amount of nitrogen also present. As you know, in the previous lecture video also discussed that it is 79 by 21 its mole basis, that is basically 3.76. Here it is, that's why 3.76 is written. Okay, so and the product is given in the carbon dioxide, oxygen, carbon monoxide and nitrogen. So the volume of product is given as 10.02%, okay, 5.62, 0.88 and 83.8%, 48%. Okay, and there are some amount of water also obviously present. Okay, now you have to, as you know that in stoichiometric ratio, or basically stoichiometric ratio is coming from the idea that is conservation of mass, means reactant of total mass of reactant is equal to total mass of obviously product. So it should be consist in the left side of the equation to right side, means in the left side of the reactant is equal to right side of the product. So this is the reaction, this is the reaction equation, the C8H18 octane plus O2 plus 3.76 N2. There's some percentage AX up there, so that it can easily combination of there, easily it can follow that the two equations are consistent. Okay, so 10.02 it is given, 0.88% CO it is given, 5.62 it is also given, 83.48 nitrogen also given, but BH2, that A, B and X you have to calculate from these equations. So from the mass balance you can easily that here nitrogen is here 3.76 into A. So nitrogen, in the nitrogen 3.76, in the right side of the nitrogen is present, that is 83.78, okay, or 48, whatever. From this equation you can calculate the value of A. And similarly for carbon, carbon is your 8x. This is the carbon is 8 into xc8 and x, so that's why 8x. There are no carbon present in the reactant part. In the product part there is 10.02% and 0.88. Okay, so this summation, that will be two summation, so that will be two summation, the x will be this one, and the h, in the h portion in hydrogen, because 18x, that will be 18x is equal to 2b. Here you know that x value, that you can easily calculate the value of, if you put this value x is equal to here, then you can calculate the value of b, that will be 20.24. Now if you put all these values in this equation, it can look like this one. So as we discussed that this is the reaction. Okay, this is the reaction, or this is the equation of C8H18 means octane. Octane react with oxygen. Okay, we already calculate the value of A, B and X. So put this value A, B and X in terms of it means C18H18 means X here, that will be a 1.36. Okay, and for A will be 22.2, because of A is 22.2 already calculated regarding a mass balance, and B is 20.24. If you put these values in this equation, it is looks like this into this one. Now now this one, now suppose C8H18, now divide 1.36 in full equations. Okay, so divide all these equations. So if you divide this, you can it will be 22 divided by 1.36, it will be 16.32. 10.02 divided by 1.36, that will be 7.37, and like this way you can you can write this equation in this form also. Now, first of all, you have to calculate the air fuel ratio, actual air fuel ratio. Air fuel ratio means mass of air divided mass of fuel. So mass of air here, air is basically 16.32 into oxygen plus 3.76 into. Now mass of air in terms of 16.32 into oxygen, that is 32 plus 3.76 into N2 is basically 28. Okay, divided by mass of fuel. Fuel basically the air fuel is your octane. Now octane basically C8H18. Now C8 means carbon, that will be 12 into 8 plus H18 would be 18 into 1. So air fuel actually is equal to 9.65 kg air per kg of fuel, means per kg of for the per kg of fuel for the per kg of fuel combustion, the required air is basically 19.65 kg. Okay, now this is the actual. Okay, now minimum air. Now in the second part of the numerical, you have to calculate the theoretical air. Okay, when you calculate the theoretical air, you have to calculate the minimum air required for the complete combustion of the fuel, and that can be done or that can obtain by the equation that C8H18 plus 12.5 O2 plus 3.76 N2 is equal to 8 CO2 plus 9 S2 plus 47 N2. So this is the equation, that from that equation you can calculate the minimum air required for the complete combustion, that is basically theoretical air. Now that from this equation, if you calculate the air fuel ratio, means mass of percentage of theoretical air, that will be mass of air actual divided mass of air theoretical. The mass of air actual, that is basically your 16.32. Okay, mass of air, that will be 16.32, and the mass of air theoretical, that is equal to 12.5 here. So that will be 131%. The theoretical air will be 131%. Okay. Now in the last part of the numerical, you have to calculate the air fuel stoichiometric. Now air fuel stoichiometric, when you calculate, that will be mass of air divided mass of fuel. For the stoichiometric, for the chemically correct air fuel ratio, if you put this, if you apply this equation and put this equation, mass of air is equal to 12.5 into O2 plus 3.76 N2 in terms of oxygen and nitrogen. If you put this, oxygen is 32 and nitrogen is your 28, then you can calculate the MA, that is basically MA, and MF basically your C8H18, that is nothing but your 12 into 8 plus 18, that will be stoichiometric, that's equal to 15.05. Okay, now this is a stoichiometric ratio, that is 15.05. And as you know, when you calculate the equivalence ratio is nothing but is the ratio of air fuel stoichiometric ratio divided by air fuel actual. So air fuel stoichiometric is basically, it's already calculated, that is 15.05. If you put here, that's 15.05. Air fuel actual, that is 19.65. Okay, so that is basically 5, means equivalent ratio is basically 0. That will be calculated. If you calculate, you can get the value of 0.76766. Okay, so it is basically less than 1. Now if it is less than 1, that means a lean mixer. Okay, if phi less than 1, that means it's a lean mixer. If phi is greater than 1, that means rich mixer. If phi is greater than 1, that is stoichiometric ratio. Okay, now here 0.766, that means the mixer is lean mixer. That means in a particular mixer, the amount of fuel is very less compared to the air, because there are chances to present actually high amount of or excess air. Okay, that's why that indicates this expression that phi is equal to 0.666. Okay, thank you very much for listening and watching me, and goodbye.